Hello class, week 13 guided notes. This is our fourth unit on fractions and operations with fractions. And today we'll primarily focus on division, both partitive and quotative, but with fraction or non-whole divisors. Before we do that though, let's do a little bit of discussion about multiplicative comparisons and reciprocal fractions. Okay, so we have a red strip and a green strip depicted here in this image. Determine which of the following tasks are equivalent. So that we have tasks A through H. Resolve all distinct tasks while avoiding mixed numbers. Okay, so let's start with task A. How many green strips make a red strip? Okay, so we have a green strip I'll outline it with this little rectangle. So there's a green strip. And the question is, if you were to take that green strip and ask how many of them does it take to give you the length of the red strip, you can see that 1, 2, 3 green strips is going to be too many. So we don't need a whole number of green strips to make the red strip. We need 2 and then some portion of the green strip to finish this out. So we have 1 green strip, 2 green strips, and then here we can see 2/3 of a green strip are needed to finish the red strip. Now I'd like to do this though without using mixed numbers. So instead what I'm going to do is I'm going to actually find out what 1/3 of a green strip is, scale it down to this amount right here. So go from the green strip down to 1/3 of the green strip, and then see how many of those it takes to make the red. And then we can see 1, 2, 3, 4, 5, 6, 7, 8 of those. So I'm going to do this two-step process of scaling down and then iterating. So partitioning and then iterating. If I start with the green strip, and I'm going to just put the word G here to stand for the green strip, and I do 1/3 of it, that'll get down to that unit amount. So this amount right there is 1/3 of the green strip. And then once you have that amount, then we had to do 8 copies of that. So we essentially do 8 copies of 1/3 of the green strip, and that means that we are doing 8/3 of the green strip. And that's how we get a length that's the same thing as the red strip. Now we're avoiding mixed numbers. So I was tempted to say 2 and 2/3, but I like this idea of taking this green amount here, scaling it down to 1/3 of its size, and then iterating that 8 times to produce the red strip. Question B, how many red strips make a green strip? Well, a red strip is all the way across here. So roughly, this is good enough. So we have a red strip, and you can see that one red strip is already longer than a green strip, so we don't need more than one red strip to make the green. We have to do a part of the red strip. And if you look at these units here, we don't know how long these are, but we can just call them units. 1, 2, 3 units out of the total 8 units that make the red. And so we see that if I were to take the red strip, which is this long. Oops, I wanted that to be a rectangle, not a... Let's start with the rectangle. There we go. So we're going to start with the red strip. We're going to scale it down by 1/8. We'll do this in a two-step process. Get down to this size, and then iterate that size 3 times, and it'll give us the green. So if I start with the red strip, and I do 1/8 of it, and then do 3 copies of that, in other words, if I do 3/8 of the red strip, I will get the green strip. And this answers question B. Now I want you to notice the relationship to go back and forth from one strip to the next. To start with the green and produce the red, I had to do 8/3 of the green. To start with the red and then produce the green, I had to do 3/8 of the red. Notice these fractions are the same numbers, but the numerator and denominator have switched. This is called the reciprocal, by the way. So if ever you see a fraction like a over b, and then you switch the role of the numerator and denominator, say b over a, these are called reciprocals of each other. Reciprocals. This is a new word. Well, I'm sure you've all seen this word before, but for students, this would be a new word. Or grade schoolers, it would be a new word. Okay, so reciprocals. And so this is not a coincidence that to go from green to red, whatever fraction winds up being here, it's the reciprocal fraction that will take you from red back to green. I'd like you to ponder that and see if that's always going to be the case. If I were to maybe draw different length strips and then figure out one fraction, and as soon as you figure out what this fraction is, you should be able to determine that the reciprocal fraction will be the way to reverse that process. Okay, let's go to question C. Measure the length of the red strip in terms of the green strip. That sounds a lot like how many greens make red. So we're saying how long is the red, and we're saying the red strip is how many units long, but measured in green strips. So this is like those tasks we did, like if this is 1 meter, then how long is the red? Right? Then we would do 1/3 of a meter and then do 8 copies of that. In other words, do 8/3 of it. So it seems like question C is just another way to do this first part. So I'll put a C here as well. 1 red is equal to 8/3 of a green. So we've measured the red in terms of green. If we measure the green in terms of red, then we get the reciprocal relationship. So this statement right here is a way to say that we've measured the green in terms of red. We said 1 green is how many reds, and it's 3/8 of a red. So that answers question D. Question E is determine the scale factor that scales the red length to become the green length. So a scale factor, if you recall, is a unitless multiplier. So when you see question E, it's like saying, let me move these over just slightly. When I look at question E, determine the scale factor that scales the red. So I'm like saying, hey, what do I have to multiply the red by so that it will produce a length that's the same thing as the green? So question E is solving this for the question mark. And that, of course, is solved by this statement down here. How many reds make green? How do you scale the red to make a green? And so question E is also answered by this bottom statement. Question F. Determine the scale factor that scales the green length to become the red. So that's question F is like saying, okay, what do you have to multiply the green by to make the red? And that we've already determined right here. You have to do 8/3 of the green. So that first line answers question F. Question G. The green strip is how many times as long as the red? Well, just translate that exactly as you read it into a math sentence. So the green strip is equal sign how many times as long as the red. So if you read question G that way, you would say G is question mark times R. So how many reds make green, in other words? And that was answered down here in this question. 3/8 of a red make a green. So question G is the bottom work, the bottom answer, is answered by the bottom answer. And finally, question H. If you were to take question H and just literally translate it into a math sentence, the red strip is how many times as long as the green strip? So we're trying to figure out how to scale the green to make the red, in other words. And that is answered by this first statement. R is 8/3 of the green. So question H is answered by the first statement. So you can see there's a variety of ways of asking the same thing. And so in the end, there are really only just 2 different distinct questions that we asked here. And we noticed the reciprocal nature of the fractions that scale G into R, and then the reciprocal that would scale R back into G. Keep in mind that in this image, if I were to do a strip that's this long right here, there's not one way to say how long this is. Right, this length right here, you could say it's one of 2 things. You could say it's 1/3 of the green, or you can say it's 1/8 of the red. It just depends on what you're looking at as the referent whole. Question 2. Now I've gone ahead and I've drawn a lot of pictures ahead of time to save time during this video lecture. If you want to pause the video and draw some of these pictures, I recommend you do that for your notes. and then you can resume the video to catch up. Okay, so we are here to determine the scale factor needed to scale each amount to the indicated value. So this first one right here, we want to scale 4 miles to 1 mile. So I've drawn a picture of something that represents 4 miles, and then I'm drawing a picture of something that represents 1 mile. And the question is, in order to produce this length, how do I scale 4? I'm going to leave the units off. How do I scale 4 so that it becomes 1? You know, what's that unitless scale factor we need right there? And clearly, 4 copies of 1 make 4, so 1 is 1/4 by the definition of a fraction, right? A fraction multiplier. To say that you do 1/4 of something means you partition to 4 pieces and keep only one of those pieces. So the answer to this question was, maybe I'll phrase it this way. I'm going to put the work right here and put a question mark right here. Say, how do I scale 4 to make it 1? And the scale factor we need is a 1/4. That's our question mark. Okay, now let's scale 4 to 8 miles. Now a lot of you will recognize right away that if you just double, like if I put a question mark and a 4 and then an 8 over here and say, hey, how do I scale 4 into 8? Most of you will just say do 2 times 4 and you get 8. But I want to show you how to do this as a 2-step process. I want to first scale 4 to 1 and then 1 to 8. So if we start with 4 miles, ultimately we are trying to solve this problem right here. How do you scale 4 to make it 8? If I start with 4 and I first do 1/4 of it, that'll make it 1. So that's how we go from the black to the green. Do 1/4 of the black. But once we have the green, now we want to do 8 of those. And then you simply combine the 2 multipliers into 1 multiplier. Remember, multiplication is associative. So you could say 8 1/4 just means 8/4. So we're really just saying do 8/4 of 4. But 8/4 is the same thing as 2. So this is the same thing as saying, same thing as saying do 2 of 4. And so the answer to our question is a 2. Let me go ahead and put our answers in boxes. There's a lot of writing here. Okay, next we want to scale 4/7 to 1 gallon. That's similar to what we did up here, except for different units. Scaling 4 to 1. So we scale the whole number back down to 1. You're going to see in this whole first column we're trying to scale back to 1. But now we're working with starting with a fractional amount. We have 4/7, and we want to scale it to 1. So I've drawn a picture here that represents, I've shaded 4/7 of a gallon. So this entire rectangle right here represents 1 gallon. I'm going to do this by first taking the shaded part that we're focused on right here and scaling it down to this single unit, which is 1/7 of a gallon. And then I'm going to expand that to reconstitute the entire gallon. So we see this as a 2-step process. We are trying to solve how do I scale 4/7 to make it 1. Okay, so we start with 4/7, and I first do 1/4 of it. All right, that's how I go from what's shaded right here down to what's shaded right there. Do 1/4 of what I started with. But now that's too small. That's only 1/7 of a gallon. So I need to do 7 of those to get back up to 1 gallon. So then we're going to follow that by doing 7. And then again, you can multiply the multipliers together. And this is the same thing as saying do 7/4 of 4/7. And that will give us 1. And this is our answer. Okay, I want you to look at the 2 so far that we've done where we scaled to 1. Not necessarily where we scaled to something else, but focus here. When I want to scale 4 to 1, I effectively multiply it or scale it by the reciprocal of 4. So that's the question mark had to be a 1/4, which is the reciprocal of 4. To scale 4/7 back into 1, I had to scale it by, I wrote the wrong thing here. That should be 7/4. We have to scale it by the reciprocal, 7/4. Keep that in mind, and we'll do let's go ahead and do this one first now, just to keep up this pattern. Okay, so we're going to scale something more than 1 back down to 1, and I have a non-whole amount, 2 1/3 containers. All right, so that would be 1 container. So we have 2 2/3 containers, and I want to scale it down to 1 container. So I'm first going to scale it down to 1/3 of a container, scale it down to that unit. So we're starting with 7/3, and I want to scale it down to 1/3, so I'm going to have to take 7/3 and first do 1/7 of it. That'll get it down to 1/3. And then once it's 1/3, then I just need to iterate that 3 times. So then do 3 copies of that, combine the multipliers, and we're effectively saying that you have to do 3/7 of 7/3 to get it back to 1. All right, so when I asked the question, how do you scale 7/3 so that you get 1, the answer to this question is to do 3/7 of 7/3. So again, we see the reciprocal nature. It's really that easy to take any amount of something and you want to scale it to 1 of that thing, you simply scale it by the reciprocal of what you started with. And once it's 1, it's easy to scale to other numbers. For example, if I want to scale 4/7 of a gallon to 3 gallons, I'm going to do this as a 2-step process. Ultimately, my goal is this. How do I scale? What do I multiply 4/7 by to get 3 gallons? Right, this is what I'm trying to solve. How do I scale 4/7 to make it 3? Well, we're going to start with 4/7 and first scale it to 1. To scale it to 1, you multiply by its scale by its reciprocal. And once it's 1, so that takes us from this step to this step. To go from 4/7 to 1, you multiply by 7/4. That's really just a 1-step summary of this 2-step method that we did here. So we did this, and we went from 4/7 to 1 in 2 steps here on the left. But now I'm just summarizing to go from 4/7 to 1. I'm showing it as a 1-step. But once you have 1 gallon, which we have right here, how do I scale that to 3 gallons? Well, just triple it. So then now I want to multiply by 3. And you can see the process. Starting with 4/7, we scale it to 1 by multiplying by its reciprocal, and then we scale it to whatever amount we want by then multiplying by that number there. And so we wind up getting, and just combine these multipliers, 3 copies of 7/4 is 21/4. So we have 21/4 is our scale factor that will turn 4/7 into 3. So the answer to our question over here is we need 21/4 is the answer. That's the scale factor we're looking for. Answer. And then this last one, we want to scale 2 1/3 containers to 1/2 of a container. So we're first going to scale 7/3 containers to 1 container. So we have 7/3 container. We're going to multiply by 3/7 to make it 1 container, which is a summary of this 2-step process we did over here. But then, so what's in here now is as a 1 container, and I want to scale that by 1/2. So then multiply by 1/2. But then combine these multipliers into 1, and 1/2 of 3/7 will be 3/14. So if I am trying to solve how do I scale 7/3 to make 1/2, the answer to this question is 3/14 is the scale factor we're looking for. Okay, let's go on to the next. Now we're going to start doing some partitive division with non-whole divisors. We're going to have several tasks for this before we switch over to quotative division. And also I'm going to go with the context of gallons of water in containers for all of these tasks, just to keep consistency. Recall that partitive division resolves a missing multiplicand multiplication task. It is the interpretation of A divided by B as the operation that answers B copies of what amount make A. Now this is a true way to interpret partitive division, even if A and B are not whole numbers. For each task below, draw an image to support your reasoning. Also express each task as both a missing quotient division task and as a missing multiplicand multiplication task, each with units. All right, so here's our scenario. We have 11 gallons of water, and it fills 5 identical containers. Determine how much water is in each container. Okay, so a few things to talk about. So I just drew a blob of water here that stands for the 11 gallons. And we want to split this up in such a way that 5 identical containers are filled. Or you could say are equally filled. You can insist that the containers here are all identical and they all get filled. Or you can insist that they're all identical, but they don't necessarily get filled. They just get the same amount, right? So if you have a bunch of containers, you just want to make sure they all get the same amount. Or you can even say that the containers are not all the same. Maybe one's big and one's small and one's medium size, but just so long as they all get the same amount, right? I prefer the way of thinking about this so that the containers are full and they're identical. So the question is going to be, how much water would there be in each of these containers? That's full. Well, effectively, we have to break 11 gallons into 5 equal parts. And one way to do that is to scale it by 1/5. So I could say that 1/5 of 11 is 11/5. So you could say that there's 11/5 gallons in each of these containers, which we could work out to a mixed number if we want, but I'm trying to avoid mixed numbers right now, but this would be 2 1/5. Another way to model this would be to draw the 11 gallons maybe as circles, right? And you can draw 11 circles, etc. And then you can say, okay, I'm going to start sharing, putting these in containers and figure out how many gallons. This is one way to do it. But I'm not going to draw that imagery. I'm just going to say we have a blob that represents 11 gallons. And that is going to be essentially equally shared with these containers and fill them up. And they're all the same size, the containers. How much water would be in each one? The answer is 11/5. Now let's frame this as a missing multiplicand multiplication task. All right, notice what we're trying to find. We're trying to find how much water is in each container. So that means we do not know how many gallons, I'll just put GAL for gallons, there are per container. Well, it's the multiplicand that has the unit that's a something per something. So that's the multiplicand. We're going to multiply this by a multiplier and get a quotient. Well, the multiplier should have a unit that matches this denominator unit. It should have a container unit. And we know that we have 5 containers. And then the end result is if you have 5 containers and there's so many gallons per container, then we want to see how many gallons total we have. And we knew that ahead of time, and we had 11 gallons total. So you can see our, let me give myself a little bit of space. You can see our multiplicative structure here with, it's the multiplier that's missing that we're trying to find. If you were to write this as a partitive division statement, it would read, you would start with the 11 gallons, and you would divide it by the number of containers, so divide it by the multiplier, which is the number of containers, and that would give us the number of gallons per container. It would give us that missing multiplicand. And then now we resolve the task. So in this case, the answer is there's 11/5 gallons per container. Now notice that today our focus is partitive division with non-whole divisors, but you'll see in this problem, right, here's the division statement, so look there. Remember, this is called the dividend, this is called the divisor, and this is called the quotient. So here's our divisor. It's a whole number. So this is not in this category of non-whole divisors. But I'm starting off with a whole divisor just to familiarize ourselves with this idea of water filling containers or partial containers and using division to answer how much there would be in one container. So now let's go to some fractional divisors. So this next scenario is we have 2 gallons of water, fills 1/3 of a container. So I've already drawn a picture of it. Determine the capacity of one container. Let's move that over. Notice how I phrased the question slightly different. Here I said, determine how much water is in each container. And here I said a different. Because currently our container has 2 gallons of water in it, but our container is not full. So if you look at this image and I say, how much water is in that container, you would probably just say 2 gallons. But if I say, what's the capacity of that container? How much water can it hold? Then you would say, well, it can clearly hold more than 2 gallons. And in fact, you can easily see here that there would be 2 gallons more needed for that third, and then 2 gallons more needed for that third. And so you can see that the capacity is 6 gallons. And that's the answer to this question. What's the capacity? Really, from this point on, we want to focus on capacity. And you could argue that I could have come up here and not asked that question, but instead I could have asked this question again, determine the capacity of one container, and the answer still would have been 11/5. That's because we are assuming that the containers were filled. Right? That word fill is important. So the amount of water in a container is equal to its capacity in this case. Here in this case, that's not true. The amount of water in the container is 2 gallons, but the capacity is 6 gallons. That's why up here I didn't want to draw these 5 containers. I didn't want to draw them all, slightly different, and then just simply say that each one had the same amount though. They all had 11/5. Because then when I say, hey, what's the capacity of the containers? Well, you're like, well, they're not all the same. So which container are you focused on? Also, you say, it's not an interesting question when you say, what's the capacity of a container when you can make that container arbitrarily large, because then there's just no good solid answer. So it's more interesting to think of this notion as that we are trying to fill containers with the water given. And sometimes we need more than one container, and sometimes we need less than one container. So this is definitely a case here where we had a container that could fit more water than we had to pour. We only had 2 gallons, and it filled 1/3 of a container. Okay, so our multiplicative and division structures are going to be pretty similar for all of these tasks. So I'm just going to copy and paste, and then we're going to erase the numbers and replace them with the relevant numbers for this task. Okay, so we're trying to figure out if we have 1/3 of a container multiplied by how many gallons there are per container, and that would give me how many gallons we actually have, which is 2. We're trying to essentially say 1/3 of what amount will give me 2. You can see why the answer is going to be 6. In division context, it'd be, okay, let's take 2 gallons and divide it by only 1/3 of a container, and this will give us how many gallons there are per container, per whole container, as if the container was full. In other words, it'd give us the capacity of the container. And the answer to this, of course, is going to be 6 gallons per whole container. Even though this container was not full. The next scenario, 12 gallons of water fills 3/5 of a container. Determine the capacity of one container. So this is a similar task. We have not enough water to fill an entire container, but we're definitely interested in the capacity. And you can probably see here, if 12 gallons fills 3/5 of a container, then each fifth has 4 gallons in it. Oops. So I can just go ahead and put a little 4G for 4 gallons in each of these fifths of a container. Right, I just divided 12 by 3. And that gave me one of these pieces. So 4 gallons corresponds to 1/5 of a container. But now I want to do the capacity of the entire container. Okay, so we're going to do that by the capacity of the entire container. each of these would also be able to hold 4 gallons, each of these fifths. So we have a total of 20 gallons. Okay, so our multiplicative and division structures, they're going to be pretty similar, just with different numbers. All right, so we have how many containers are currently occupied? 3/5 of a container. We don't know how many containers there are, or how many gallons there are per container, so that's the multiplicand. But we know that the amount that corresponds to 3/5 of a container is 12 gallons. So we're saying 3/5 of what will give me 12? So in division, it would be 12 gallons divided by 3/5 containers, and the answer will be, well, how many gallons per container there are. In other words, the capacity. And we can already see that the answer is going to be 20. We did that already with the imagery. Now I want to point out a few things about these answers. We're going to start to generalize, and you're going to see a pattern. Let me separate the question marks. I'm struggling here. There we go. Move that and move that. Okay, in this first case, notice what we did. We started with 11 gallons. And I had to find 1/5 of it because it was being shared with 5 containers. And that's what gave me the amount we had per container. But notice what you probably already know about dividing by a number. If you have 11 gallons and you divide it by 5 containers, the answer is going to be the 11 gallons, but multiplied by the reciprocal of this 5. Right, so to divide by 5 appears to be equivalent to multiplying by 1/5. And this is using a partitive division meaning. So we see the invert and multiply algorithm that you've certainly know at this point in your education, that to divide by a number, you multiply instead by its reciprocal. Notice that happened here as well. So we're doing a 2 divided by 1/3. Well, look at the imagery. If 2 gallons was what we started with, and I wanted to reconstitute the entire container, then I'm going to have to triple that to get my capacity. And so we see 2 divided by 1/3 is equivalent, will give us an answer that's 2 times the reciprocal of 1/3, times 3. And here, we had 12 gallons that corresponded to 3/5 containers. And we want to determine the capacity of the entire container. So we're going to get, we start with the 12 gallons. So I started with, the 12 gallons over here. I first scaled it down to get one of these portions. So I scaled it down by 1/3, right, divided by 3 or multiplied by 1/3. And then I had to multiply by 5 to get back up to the entire container. Let me go ahead and just leave off the unit gallon here so I have a little bit of extra space. In other words, multiply these multipliers together. 5 copies of 1/3 is just 5/3 of 12. Okay, so take a look. When we do 12 divided by 3/5 containers, the goal is to find how many gallons there are per container, and we answer that by doing the reciprocal, the reciprocal of 3/5, which is 5/3 copies of that 12 gallons. And that will give us the amount of gallons there are per container. So you're seeing the invert and multiply algorithm happen here. While we're at this stage, let me show you another way to keep track of all this stuff. Let me erase. I'm just going to erase this for space's sake. And then I'm going to shrink this image down a little bit. I'm going to give myself a little room to put a little table in here. Oops. There we go. Shrink that down. And let's go ahead and move that up and then shrink all this down a little bit, just creating some space for myself to work. Another way to keep track of what's going on here is to do a table and do tandem scaling. For example, we have a certain number of containers corresponds to a certain number of gallons. Now this table that I'm making here is not acceptable for what this said, to draw an image to support my reasoning. But I'm going to show you that what's happening with this table. You can organize the steps in this table as well. So we know that 12 gallons corresponds to 3/5 of a container. So what you want to do is boil down to 1/5 of a container. And then ask yourself, how do you scale 3/5 to 1/5? Right? To go from here to here, we scale by 1/3. And you do that exact same thing to the number of gallons. If you do 1/3 of 12, we get 4. So this tells us that 1/5 of the container has 4 gallons, right? Which is what we're seeing here. And now we want to scale 1/5 back to up to 1. So to scale 1/5 to 1, we have to scale by 5. We have to do 5 copies of a fifth in order to get to 1. We do that exact same scale factor over here by 5, and that will tell you that 1 container corresponds to 20 gallons. This is called tandem scaling in a table. You start with any number you want right here. First scale it to a unit fraction, and then scale it back to 1. And whatever scale factors you need to accomplish that, you do the exact same scale factors over here to the number of gallons, and you can, in the end, conclude how many gallons correspond to 1 container, which is really what we're after, the multiplicand. Okay, here we have 5 gallons of water fills 1 1/3 identical containers. Determine the capacity of 1 container. Okay, you're probably getting a sense for how to do this pretty well. Everything that you see here in blue is 5 gallons. So the question is going to be, how many gallons are there in each of these blue parts? Also notice it's good to think of 1 1/3 as 4/3. So you can actually see 1, 2, 3, 4 equal parts, 4/3. But the question is, how much water is in each of those thirds of a container? Well, if the total blue that you see here is 5 gallons, then we want to divide 5 into 4 parts. So each of these will have 5/4 gallons. But then you want to put 3 of those 5/4 together to get the capacity of 1 container. So that's going to be 15/4. And that's the answer to our question. There's 15/4 gallons per container, if 5 gallons fills 1 1/3 containers. As far as this work here, let's just, to save time, copy and paste again. You're going to see a lot of similar multiplicative structures going on. Give myself a little more room, move that over. Okay. Oops. Got that free floating 1 right there. 15. Okay. So we have erase, 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 erase. Okay. We have 4/3 containers. We don't know how many gallons there are per container, but we know the total is 5 gallons. So to use division, I would do 5 divided by 4/3, and that would give me how many gallons per container we have, or that we're looking for. And the answer to this is, well, start with the 5 gallons, first do 1/4 of it, and then do 3 of those. In other words, just do 3/4 of 5 gallons. In other words, we get 15/4. gallons per container. But again, notice 5 divided by 4/3. To answer this with a partitive conception, we do 3/4 of 5. If you were to do this with the table, containers, gallons, and you can even do this in a one-step. We know that if you have so many containers, we had 4/3 containers, and the goal is to get down to 1 container. And 4/3 container corresponded to 5 gallons. You could do the two-step process where you do 1/4 and then times 3, or you can recognize that you scale to turn 4/3 into 1. You scale by its reciprocal. So do the same scale factor over here, and 3/4 of 5 is the 15/4. Next one, 12/5 gallons of water fills 3/8 of a container. So here's our imagery. Determine the capacity of 1 container. Okay, so I'm going to have to take 12/5. That fills 3/8 of a container. Figure out how much water is in one of these 3 parts. So divide 12/5 by 3, or in other words, multiply 12/5 by 1/3. And that tells you that there's 4/5 gallons in each of these parts. And then the question is, how much would be in the entire container? Well, we'd have to do 8 copies of 4/5 to reconstitute the entire container. For time's sake, is it okay? I'm going to stop copying and pasting these multiplication statements. Maybe I'll do it. Why not? Copy and paste doesn't take too long. Oops, I didn't want to erase that question mark. Okay, so we had 3/8 containers. Don't know how many gallons per container, but we know that 3/8 gives us 12/5 gallons. So I would do 12/5 gallons and divide it by 3/8 of a container, and that would represent the amount of gallons per container. And I'm going to leave the units off here. Pull that off to the side. Okay, so we start with the 12/5. I first do 1/3 of that to get it down to a 1/8 of a container, and then I do 8 of those to reconstitute the entire container. In other words, I do 8/3 of the 12/5. And that winds up being 8 times 32. I do the 1/3 of 12/5 first and get 4/5 and do 8 of those, so I get 32/5 gallons per container. As my answer. I'm going to leave off doing the table and scaling in tandem. Okay, one more. 3/4 of a gallon of water fills 4½ containers. So I drew an imagery of this. 4½ containers is really 9/2 containers, and all the blue is 3/4 of a gallon. So I don't know why I erased that. Just leave that there. So my question is, how much is in just one of these halves of a container, right? How much is just in there? Well, count how many parts there are of all the same size. There are 9 halves here. So take 3/4 and do 1/9 of it. So I would do 1/9 of 3/4. That is 3/36, which is 1/12. So we have 1/12 of a gallon in each half container. All right, so if I focus on one of these containers, there's 1/12 of a gallon here, and there's 1/12 of a gallon here. So in one container, the capacity of one container is 2/12, which is 1/6 of a gallon. On this previous one, again, notice the invert and multiply algorithm happening here to get an answer. Let's put that there. Erase, that's new, that's going to be new, that's new, new. Oh, that's new. Okay. So we had 4½ which is 9 halves containers. times an unknown number of gallons per container will equal the, and how many gallons did I start with? We started with 3/4 of a gallon. Okay, so the division would be 3/4 of a gallon divided by 9/2 containers, and the question is how many gallons per container? Well, we start with the 3/4 of a gallon, right, which was all the blue, and I did 1/9 of that to figure out what was in each half container, and then double that to figure out what's in each entire container. In other words, we did 2/9 of 3/4. And you'll notice the invert and multiply algorithm happening here. And of course, this gives us 6/36, which is 1/6 gallon per container. Okay, let's generalize now. If I'm taking some amount, and this amount A could be a fraction or non-fraction, doesn't matter what it is, it's just some amount of water, and you're dividing it by this many containers, to stick with the water and containers analogy or scenario, and we want to determine the multiplicand, which is how many gallons there are per container. So our goal here is to scale containers to 1 and then do tandem scaling and see what happens to get, or what amount of gallons we get when we have only one container. And you can do this in a 2-step process or a 1-step process. Let's do 2 steps. Let's scale by 1/c. So if I have c deths, scale by 1/c will take it down to just 1/10 of a container. And then we do the exact same scale factor to A. So if I would do 1/6 of A. But now I want to get up to 1, so I do one more step. And now we want to scale by D, multiply by D. We'll do the same scale factor over here. That will take 1/10. Oops, 1/10 will be turned into one container, and we multiply by D. And of course, this is the same thing as doing d/10ths of A. So what we're seeing is that if I put units on this, if I had A gallons and I divided that by C/D containers, then I would get how many gallons per container? Well, I would get D/C times A gallons per container. And this gives us the invert and multiply algorithm for any divisor, right? It doesn't matter if A is a fraction, this could be a fraction or a whole number. But when you're dividing by a fractional divisor with a partitive meaning, then you do the invert and multiply to get the missing multiplicand. Okay, now let's jump to quotative meanings. Quotative division with non-whole divisors. Okay, so recall that quotative division, or called measuring division, resolves a missing multiplier multiplication task. It is the interpretation of A divided by B as the operation that answers how many copies of B make A. This is a true way to interpret quotative division, even if A and B are not whole. For each task below, draw an image to support your reasoning. Also express each task as both a missing quotient division task and as a missing multiplier multiplication task, each with units. So again, we're sticking with water and containers and capacities of containers. And now we know the capacity. So the capacity is given. I'm also going to just do whole numbers here for this first page. The capacity of a container is 5 gallons. And notice I have asked several questions here. Let's just focus on this first one right here. Let's focus on the scenario. Pretend you're pouring the water out into containers, and you pour until you fill, and then you move on to the next container. All right, so we're going to get 5 gallons. We're trying to fill containers. We have 11 gallons of water to dispense. Okay, so we have 5 gallons go into the first container. That's just going to be copied. 5 gallons are going to wind up into the second container. That's 10 gallons so far. We have only 1 gallon left. Well, this final gallon won't fill up this last container. How much of it will it fill up? Well, we have 1 gallon, and the container holds 5 gallons, so that's 1/5. of the container. So I'm going to break this container up into 5 equal parts, roughly. We'll say that's good enough. And we just managed to get one, it's a little bit too thick, one of those parts manages to get full with that final amount. That's just 1 gallon right there. Okay, so there's our 11 gallons. And the question was, determine how many containers are needed to hold 11 gallons. Well, to answer the first question, how many containers are needed? Well, we needed 2 wasn't enough, right? We needed a total of 3 containers to contain this whole. So I would answer that first question and say 3 containers needed. And we're assuming all the containers are equal. They're identical. We could also say, what's the minimum number needed? Because I suppose you could have identical containers and just put, put 2 gallons here, 2 gallons, and kind of spread them out and say, here, I used 5 containers. But keep in mind that we're trying to fill the containers. We're pouring water into a container until it's full before we move on to the next container. And so this would give us the minimum number of containers needed, which is 3. Okay, now let's read the second thing this is asking. Determine how many containers are filled by 11 gallons. Okay, so look at our situation. How many containers are filled? Well, only 2. 2 containers are filled. Right, the third one was not, but we still needed it, but it wasn't full. Then let's read this last sentence right here. Determine how many containers are required to hold 11 gallons. Fill as many containers as possible, and if any container is not filled, express what portion of that container is filled. So here we would say, okay, so we have 2 full containers, and we have 1/5 of another container. And I'm resistant to use the word filled. Maybe we could use the word occupied here. By water, H2O. Because when you use the word filled, it makes you think that, when I look at this, I don't think of the word filled, but you could focus on just 1/5 of the container and say that part is filled. So if you want to put the word filled here instead of occupied, that's fine too, as long as you realize that technically the entire last container is not full, but 1/5 of it is full. So 2 1/5 containers are occupied by water, or 2 1/5 are filled by water, if you want to say it that way. Maybe to distinguish with this one here, we could say 2 containers are completely filled. Maybe that helps distinguish from any partial filling. So as you can see, there's lots of different nuances in the language that could make children think that you're asking one thing, when in reality you might have been trying to ask something else. And so that's the whole purpose of me phrasing, saying find this, but then find this, and then next find this. And to some people, you might sound like you're just asking the same thing. But I wanted to show you how you might phrase the question slightly differently to evoke slightly different ways to answer this question. Now, the way moving forward that we're interested in, when we're trying to find a missing multiplier, is we're focusing on this last one. I want to know how many entire and partial are occupied by the water. Okay, so let's take a moment and write down what this would look like as a missing multiplier task. All right, so once you see that the capacity is 5 gallons, that tells us that we know the multiplier. So let me actually just copy this structure, bring it down. Okay, let's get rid of even the question marks and kind of start from scratch. What's going on here? Just goodbye, all of this. Okay, we know that the capacity is 5 gallons container. That's what we know. Determine how many containers, including partial containers, would make 11 gallons. So we know the result is to be 11 gallons, and we're trying to figure out the number of containers. So this is definitely a missing multiplier way of thinking. So when I do the division, I would do 11 gallons and divide it by the multiplier, or sorry, divide it by the multiplicand. So we're going to divide it by the fact that there are 5 gallons per container, and our answer is going to be containers. It's going to be a multiplier. And we can see that the answer is 2 1/5. Well, 2 1/5, of course, this is the same thing as 11/5. So I'm going to avoid mixed numbers and say 11/5 containers are occupied by 11 gallons when each container holds 5 gallons. Now, if you take the first statement right here and just sort of get rid of the units and think of this as scaling, unitless multipliers. And you say, okay, I want to scale 5 gallons to make it 11 gallons. I'll go ahead and put the G here for gallons. This is another valid way to think about this. You know, take the idea of containers out of it and just say, how do you scale 5 gallons to make it 11 gallons? Well, if you do this as a two-step process, you would take the 5 gallons, scale it to 1 gallon, so multiply by 1/5. Now that's 1 gallon, but then multiply by 11, and that will give you 11 gallons. In other words, combine these multipliers, you have a scale factor of 11/5 times 5 gallons will give you 11 gallons. And in other words, we have found the answer. So if this was red, then the answer to this question is this multiplier right here. So the answer is 11/5. Right, is exactly what we got here. If you put containers back into our thinking, then it's 11/5 containers. If you just think unitless scaling, unitless multiplier scaling, like how do you scale 5 gallons into 11 gallons? The answer is 11/5. Or you can say, you know, how many copies of 5 make 11? This is what quotative division asks, right? How many copies of the divisor make the dividend? How many copies of 5 make 11? And the answer is 11/5 copies of 5 make 11. Okay, next one. The capacity of a container is 5 gallons. Determine how many containers are needed to hold 3 gallons. Okay, well, 3 gallons is, if we have a container here that holds 5 gallons, if I were to break this up into 5 equal parts, then each part would correspond to a gallon. We'll say that's good enough. But then we actually have 3 gallons. Okay, so a container can hold more than the water that we have. That was not the case up here, right? Up here we needed more than one container to contain all the water. Here we need less than one container to contain all the water. But this is still a missing multiplier task, because you're saying how many containers. So let me just copy paste instead of rewriting all this. And we know that the capacity is 5 gallons per container, but we want to produce less than 5. So we expect a fractional multiplier that's less than 1, so that we can shrink 5 to 3, essentially. And then here the numbers would be different. We would say, okay, we have 3 gallons divided by 5 gallons per container. So we're trying to scale 5 to 3. Essentially. We're still going to do 1/5 of 5 to bring it down to 1, and then do 3 of those to get it back up to 3 gallons. So in other words, if we do 3/5 of 5 gallons, we'll get 3 gallons. So the answer is that red 3/5. 3/5 of a container. That's how many containers are needed to hold 3 gallons if each container can hold 5 gallons. You only need 3/5 of that container. You know, in a case like this, is identical to asking, hey, what in this picture right here, like what fraction of the whole is shaded in. 3/5 of the whole is shaded in. So 3/5 of a container is occupied by water. All right, now let's do a capacity that is less than a gallon. Determine how many containers or partial containers will hold 4 gallons. So I drew a whole bunch of containers. Each of these is a container. So there's one container, and that holds 1/3 of a gallon. Well, if you take 3 containers and put them together, then I see that an entire gallon of water is used. And we need to hold 4 gallons. Right, so I've drawn the adequate number here. I'm just going to group them together. I'll just go ahead and delete that and just copy this. Okay, so I regroup them, and we can see that we have 3 containers right here, 3 containers right here, 3 more containers, and 3 more containers. And each of these 3 containers corresponded to 1 gallon. So we can see that we have the 4 gallons and how many containers was needed. And you can see there's 12 containers here. Okay, so let's copy this structure. Erase, we don't know the multiplier. Let's see, we're going to different numbers throughout here. Okay, there we go. So we don't know how many containers we need. We know that each container holds 1/3 of a gallon per container, and we want to reconstitute 4 gallons. So the division statement would be 4 gallons divided by 1/3 of a gallon per container, and how many containers does that yield? So I want to be consistent here. I was supposed to write these as missing quotient tasks. There we go. And then the answer is 11/5 gallons, or containers. So let me actually go back up to here and circle some answers. This was supposed to be a question mark initially, and then the answer, though, of course, is 3/5 container. Get some answers here. Okay. All right, so effectively we are trying to, if you look at this first statement here, we're trying to scale 1/3 into 4. All right, so we're starting with 1/3 of a gallon, and I want to scale it to 4. Well, first scale it to 1 gallon. So to scale 1/3 of a gallon to 1 gallon, you need to triple it. That takes it to 1 gallon. Now, if you next multiply by 4, that, of course, will take us to 4 gallons. And then combine these into a single multiplier. So if we do 12 copies of 1/3 of a gallon, we will get 4 gallons. And the question mark is right here. So that's the answer to our question. So we know that 12 containers are required. Let's see, what's going on here? Oops, this actually worked out this entire problem before. Let me delete all this stuff real fast. Just delete. Okay. So we have the capacity of a container is 1/3 of a gallon. Determine how many containers or partial containers will hold 1/5 of a gallon. Okay, so let me just get rid of this whole imagery. That's revealing a little bit too much. This one's a little bit harder to think about initially. We have 1/3 of a gallon in each container. That's how much it can hold. And we want to know what fraction of that will only be 1/5. Now 1/5 is less than 1/3 of a gallon, so we know that not an entire container. So if we draw this entire container, we know that its capacity is 1/3 of a gallon. And some lower amount will be 1/5. The question is how much lower? Like what portion of this container is full? Well, in a case like this where we have fractional amounts for the whole amount and for the partial amount, it's good to get common denominators. So we can say something like, okay, if 1/3 of a gallon is the capacity, and I look at the two denominators here, 3 and 5, 15 is the least common denominator. So I'm going to make, instead of saying that we have 1/3 of a container, I'm going to say that we have a total of, oops, my thumb hits the wrong thing sometimes. We have a capacity of 5/15. In other words, I want to break this container into 5 parts. So each part will be 1/15. So I'm going to do that next. Okay, we'll say that's good enough. So each of these is 1/15 of a gallon. And let's do that by putting it here. 1/15 of a gallon for that part. It's 5/15 divided by 5. And we want to get up to 1/5 of a gallon. Well, 1/5, get a denominator of 15 on that, is 3/15. So I need another 15th of a gallon and then another 15th of a gallon. And that's how much should be shaded. And that's how much water we actually have in here. It's 3/15, which is the same thing as 1/5 of a gallon. And our capacity was 5/15, or the same thing as 1/3 of a gallon. So this is really the best way when your denominators don't match, is get them to match. And it's easier to analyze the situation. Now we can see very clearly that 3/5 of the container is full. So now the answer is going to be 3/5 of a container. But let's go ahead and copy this structure down. Good enough, okay. We see we don't know, but leave the question marks as question marks. Let's change all these things. Okay. How many containers? We know that 1/3 of a gallon there is per container, and we're going to wind up producing only 1/5 of a gallon. So we're scaling 1/3 down to 1/5. So we know that our answer is going to be less than 1. And it's 1/5 of a gallon divided by 1/3 of a gallon per container. So let's start with the 1/5. Or sorry, 1/3, the entire capacity. I'm just copying this structure, but with less units. So question mark times 1/3 of a gallon equals 1/5 of a gallon. And there's lots of ways to do this. You can scale down, then scale up, or scale up, then scale down. Let me show you a scale up, then scale down approach. If I multiply by 3, then I'll have 1 gallon. Agreed? But now I want to get it down to 1/5, so multiply by 1/5 next. And that would give us 1/5 of a gallon. Or you could have reversed that. You could have done 1/5 of 1/3 of a gallon, which is what the imagery shows, right? Here's 1/3 of a gallon right there. 1/5 of it is one of these. And then we'll do 3 of those to reconstitute how much water we actually have. So you could have done this approach as well. Do 1/5 of 3 gallons and then do 3 of those. And that also will produce 1/5 of a gallon. Doesn't really matter. If we were to stick with the way we've been doing it in the past, is get 1/3 of a gallon back up to 1, and then scale 1 gallon down to the amount of gallons we actually want. But when you multiply, when you do 1/5 of 3, that's the same thing as doing 3/5 of a third. And that's how we'll get to a fifth. All right, so the question mark is this roll right here. That's what we're trying to answer. So we just discovered that 3/5 of a container is occupied by water when the container can hold 1/3 of a gallon, but there's only 1/5 of a gallon in there. This is a quotative division task. It's how many copies of 1/3 make a fifth, and the answer is 3/5 copies of 1/3 will make 1/5. All right, for the rest of these quotative division tasks, I'm going to get away from actually drawing containers in water, and I'm going to start using number lines to represent these amounts. For example, determine how many containers or partial containers will hold 8 gallons if the capacity of a container is 4/3 gallons. Okay, so one strategy is draw or look at both of these numbers and just decide which one's larger. The 8 is larger, so I draw that first. So I've drawn a number line to represent 8 gallons. And so each of these bars represents 1 gallon. And there's 8 of them. And our goal is to figure out how many copies of 4/3 make 8. Right, because each container holds 4/3, and 4/3 is less. So I'm going to go in here and start doing thirds in here. So break each of these gallons into thirds by putting 2 little red hash marks, or whatever color, whatever, smaller hash marks in between. And then start measuring out 4/3 gallons. Well, 4/3 gallons would take me to that hash mark. Let me draw this a little bit better, because I'm going to copy paste. And 4/3 gallons corresponds to 1 container. So there's a container's worth of water right there. And then just keep marching along. The next 4/3 will take me to that red hash mark, another container. The next 4/3 will take me to a whole number of gallons. If I do 3 containers and each container holds 4/3 gallons, then we're going to get 4 gallons total, right? Which is, in black, is keeping track of the gallons. So there's 1 gallon, 2 gallons, right? 3 gallons, 4 gallons, 5 gallons, 6, 7, and then finally our 8 gallons. So we just have to keep this up. And notice in this particular case, we wind up getting a perfect number of containers. A whole number of containers winds up being adequate. We can see 8 containers here. 8 containers times 4/3 gallons per container will give me 8 total gallons. Let me shrink this down just so we have enough space. You can zoom in and look at that in more detail. Okay, so now we've got, we don't know how many gallons per, we do know these things, but let me erase all this stuff for this problem. Okay, so we don't know how many containers. We know that there's 4/3 gallons per container, and we want to reconstitute 8 gallons. So this is like saying how many copies of 4/3 makes 8. And so we would do 8 gallons divided by 4/3, and that's the division that would answer this question. And we're going to get there by scaling. We're going to start with 4/3 gallons. If I scale that down to 1 gallon, so multiply by 3/4, we'll get it to 1 gallon. And then scale it up to 8 gallons by then multiplying by 8. And that will give us 8 gallons. Combine these multipliers. 8 copies of 3/4 is 24/4, which is 6. So in other words, 6 copies of 4/3 gallons will give us 8 gallons, which is exactly what we see here. 6 containers is our answer. how many containers, partial containers, will hold 2/5 of a gallon if the capacity of a container is 4/3 gallons. Okay, look at these two numbers. That's less than 1. This one's more than 1. So that's the larger number. I'm going to draw that first. But that's the entire container this time, though. Unlike up here, an entire container was less than what I had to. I had more water than it could fill up one container. Well, that role reversal has occurred here. There's a reversal here. This is now an entire container. It's 4/3 of a gallon. So you can see each of these is 1/3 of a gallon. Third, 4/3. So after 3/3, here's our 1 gallon mark. Okay, so 4/3 of a gallon fill up one container, and we want to do 2/5 of a gallon. That's only 2/5 of a gallon in here. So when you have these fractional amounts that have different denominators, express these in terms of the same denominator. So let me do that by doing the following. I'm going to write down copy this down. Let's delete that, delete, delete. Get rid of all this stuff. All right, we have 4/3 gallons per container, but we only want to make 2/5 gallons. We can accomplish this by saying, well, visually, there's a few ways to do this. We ultimately want to do 2/5 gallons divided by 4/3 containers. If you were to get a common denominator and express these with that common denominator, here's what this would look like. 4/3 times 5 times 5 is 20/15. And 2/5 times 3 times 3 is 6/15. So we're saying, what do I have to, how many copies of 20/15 make 6/15? Well, so I took each third and I broke it up into 5 parts. That's what the red marks are. So you can see that we start with 20/15 gallons. Or in other words, one container. So let me just put that up here. It corresponds to 20/15 gallons. Count their little red hash marks, right? 1, 2, 3, 4, 5, etc. 10, 15, 20/15. And the amount of water that's actually in this container is 6/15. So we can just go out till we have 6/15. Right, 1, 2, 3, 4, 5, 6. They're right there. That's how much water we actually have in this container, 6/15. Let's do that with blue to stand for water. Okay, so our entire container can hold 4/3 or 20/15 gallons, but it's only full with 6/15 of gallons, or in other words, 2/5. And now it's a simple question is, hey, what fraction, right? The water stops right there. Let me make that smaller. Right, what fraction of the entire container has water in it? We can see 6 parts. Each part is the little red notch to notch. 6 parts out of the 20 parts. So we see 6/20 of a container. So this corresponds to 6/20 containers. And that would be the answer to our question using with a visual aid here. 6/20, though, you could also simplify, right, to divide by 2 and 2, so 3/10 of a container. Which makes sense. If there's 20 little pieces here, across the entire container, you could pair them off, right? So you can say, going in pairs, you can see how many pairs there are. There's going to be 10 of them. Then how much is shaded by the blue, right? That's ultimately, that was up to right there. So you can see 3/10 of the container is full. Same thing as 6/20. Right? And it's also important to be able to keep in mind that there's different units for each of these lengths. Like that little length there stands for one of two things. That's 1/15 of a gallon, but it corresponds to 1/20 of a container. Just keep that in mind. We're coordinating multiple levels of units here. And the other approach, if we start with 4/3, sorry, we're trying to figure out how to scale, how to scale 4/3. I'm just copying this line right here, but with less units. We want to scale 4/3 gallons to turn it into 2/5 gallons. Well, the two-step process is to do the following. To turn 4/3 gallon into 1 gallon, you multiply it by 3/4. But then to turn 1 into 2/5, you scale by 2/5. So we need 2/5 out here as well. And then combine these multipliers into one multiplier. 2/5 of 3/4 is going to be 6/20 or 3/10. And that is how you scale 4/3 to make it 2/5. Right, so that confirms the same answer. We need 3/10 of the container is full. Okay, we just got about 4 more here. Determine how many containers will hold 7 gallons if the capacity is 1 1/4. So I looked at 7 and 1 1/4. 7 is more, so I drew that first. So here's a picture of 7 gallons. And the capacity is 1 1/4. Okay, so let's break these up into fourths as well. So in half, then half, 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 etc. And I'm going to take the approach like I did up here to start counting off the containers. Each container is 1 1/4. So we go from here to there. Is 1 1/4, which is 5/4 gallons. But that corresponds to 1 container. And now let's just start copying. Oops. That's not what I wanted to do. There we go. Okay, now look, we run out, right? Like we get down to the end and another container is not going to be completely full. So we had enough water to fill 5 full containers, but this last container only has so much water in it. So let me actually erase this and figure out just how many gallons exactly and how many containers that is. So from here to the end, where the water ends, we have 3/4 of a gallon. And if an entire container has 5/4 in it, then 3/4 out of those 5/4 will correspond to 3/5 of a container. Now, when people are answering this question, when you're not thinking about units, sometimes it's tempting to give an answer that looks like this. A student will say 1, 2, 3, 4, 5 containers. Then they see these 3 pieces here, and they say something like this. The answer is 5, and each of those pieces was 1/4, so 5 3/4 containers. And they made a mistake because they switched units. The containers applies to the 5, but to the 3/4 should be the unit gallon. This last little bit is 3/4 of a gallon, not 3/4 of a container. So that sometimes the student will just mindlessly put the first fraction they see there at the end and say 5 3/4 is the answer. Like, nope, it's not the answer. We want to give both the whole number and the proper fraction next to it, so this mixed number both have to have the same unit for you to put that unit here at the end. So instead of saying 3/4, you need to say 3/5, so that they all have container units. So 5 3/5 containers, which would be 28/5 containers. Keep in mind that each of these little hash marks, we are coordinating multiple levels of units. So this length right here stands for 1/4 of a gallon, right? Because each of the black marks represented 1 gallon. Right? There's 1 gallon there. Then there was the 2 gallon mark there, right? The 3 gallon mark. We had the 4 gallon mark right there, the 5 gallon mark, 6 gallons, and then we had the final 7 gallons. So each of these little gaps here is 1/4 of a gallon. But that corresponds to, since an entire container spans 5 of those marks, not just 4 of them, that's 1/5 of a container. And because these fractions are so close to each other, it's super easy for students to conflate them and not realize they're referring to different things. And this is why it's nice to do problems like this in a context where you can imagine a gallon and imagine a container, and so you're not bothered by the fact that 1/4 and 1/5 are referring to the same amount. It's just they're different units. 1/4 of a gallon and 1/5 of a container have the same volume. Okay, if we're doing this with the scaling approach, okay, sorry, I was looking at something. Yeah, the scaling approach, let me copy all this down. Let's shrink it down so it fits. There we go, okay. And let's see what needs to be changed here. These numbers need to be changed. In fact, I'm probably not going to bother with this line at all. Just get rid of that. Changed, all these things changed. Okay. We have 4 or 5/4 gallons per container. We want to reconstitute 7 gallons. So you do 7 gallons divided by 5/4 gallons per container. That would give us how many containers are needed. And we can do this by saying, okay, we'll start with the 5/4 gallons. That corresponds to 1 container. And scale it so that we get up to 7 gallons. Well, if I scale 5/4 by 4/5, that will take it to 1 gallon, and now I'll scale by 7 next to get it back up to 7 gallons. So 4/5 of 5/4 of a gallon is 1 gallon, and then 7 times that is 7 gallons. And then combine the 7 and the 4/5 multipliers, and we have 28/5 is the scale factor needed to scale 5/4 to 7. And that is, of course, our answer, 28/5 containers. Okay, the next one, determine how many containers will hold 1/8 of a gallon if the capacity is 1 1/4. So 1 1/4 is more. And we have a situation where the entire container, therefore, that's 1 container, is drawn here. It's 1 1/4 gallons. Right, here's our 1 gallon mark is sitting right there. Let me move that right there. So we have 5/4 or 1 1/4 gallons per container, and we only want 1/8 of a gallon. Well, notice that the gallon's already broken up into 4, so I want to break that into eighths next. So this will be an easy, just cut each of these in half. That one too, if you want. So 1 container corresponds to 5/4 gallons, which corresponds, or which is equal to 10/8 gallons. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10/8 gallons. and each of these gaps between a red and a black, that stands for, that's either 1/8 of a gallon, or you can say it's 1/10 of a container. And our water only goes up to 1/8. So 1/8 is right here. So I could actually just take this and let's move this over here. And there we go. Our capacity is 10/8, and we only have 1/8 of a gallon in there. So you can see that we have 1/10 of a container. The answer is in containers. Let me copy this one. There we go. Okay, we have 5, or how many was it? 5/4. 5/4 gallons per container. We're only going to wind up with 1/8 of a gallon though. So we're trying to figure out the scale factor. That scale is 5/4 to 1/8. In division notation, it would look like 1/8 of a gallon divided by 5/4 gallons per container. And if we start with 5/4 gallons, and we want to scale that to 1/8 of a gallon, let's start by scaling 5/4 to 1 by multiplying by 4/5. And now that it's 1, then scale by 1/8. And that will get us to 1/8. Combine these two into one multiplier, and it's 4/40ths, or 1/10. And that's the answer to the question. So I make it red because that's what we're trying to find. Right? We were looking for that scale factor. And 1/8, 1/10 is it. Okay, one more and then we're going to generalize, and this lesson will be done. Capacity is 3/5 of a gallon. We want to, how many containers will hold 2 and 4/5? Okay, so I'm going to draw the larger number first, 2 and 4/5. Well, here's 3. So I need to do some partitioning here. Let's just do everything into fifths. So the middle piece and then 2x. You're gonna have to use your imagination. Try to imagine that these are all the same. And that's where the water level actually stops. So let me just get rid of that and bring this in. Okay. So there's our 2 and 4/5 gallons, and each container holds only 3/5 of a gallon. Okay, so let me make that one look a little bit better. And it still looks bad. Somewhat better. Okay. There's 3/5 of a gallon. In other words, it's one container. We're just going to copy this and see how many containers we get. See, these are slightly off. Yeah, these are some bad drawings. I'm going to have to, copying and pasting is going to be problematic because the more inaccurate you are in doing this, the worse this gets. So let's just do this. 3/5. 1, 2, 3. That takes me to there. There's another 3/5 gallon. 1, 2, 3 takes me there. 1, 2, 3 takes me there. And then we have so you can see 4 containers are used so far. And we only have 2 little pieces left. Well, each piece is 1/5 of a gallon, so that's 2/5 of a gallon right there at the end. And each of those little pieces is 1/3 of a container, so that's 2/3 container. Right? Because each piece is either 1/5 of a gallon, or it's 1/3 of a container. So in the end, we can see we have 4 containers and an extra 2/3, so 4 2/3 containers. I'll write this as a improper fraction. That's 12/3 plus 2/3. That's 14/3 containers. All right, this is our final one. Erase, erase, get rid of. Okay. There were 3/5 gallons per container, and we wanted to reconstitute a total of 2 4/5 gallons. Well, 2 4/5 gallons is 10/5 plus 4/5 is 14/5. So we were essentially doing 14/5 gallons divided by 3/5 gallons with the quotative meaning, such as how many copies of 3/5 make 14/5, which can be phrased with a unitless multiplier. Scale 3/5 by what amount to equal 14/5? Well, to scale 3/5 to 1, you're going to multiply by 5/3. And then to scale 1 to 14/5, you're going to multiply by 14/5. And when you multiply these two multipliers together, you're going to get 70/15, which boils down to back to 14/3. So 14/3 is that multiplier we're looking for. Okay. And that's our answer, 14/3 containers. All right, now the reason, you might have been wondering, why was I bothering doing this approach after I'd already answered the question with a visual? Because I want to show you what's generalizable. And all these problems that we've done, a quotative, starting right, done a bunch. Here we go. When I want to scale a number into another number, and I'm looking for that red question mark, then first scale the 5 by using its reciprocal, and then scale this 1 right there by the same number you see there. In other words, the red answer is the product of these two things. One of the two things is the dividend, the 11 and the 11, and the other factor that's going to contribute is the reciprocal of the divisor. So if I'm looking for this red multiplier, then I take the dividend and I multiply it by the reciprocal of the divisor, and that's where this 11 times 1/5 or 11/5 answer comes from. Okay, so just focus on the reds. To scale 5 into 3, I'm looking for this question mark. Well, scale it to 1 by doing 1/5, so the reciprocal of 5, and then triple to match that number. In other words, this number here is the divisor. And this number here is the reciprocal of the, this number here is the dividend, and this number here is the reciprocal of the divisor. And you multiply those together to find that scale factor that we're looking for. Same thing's going on here. To scale 1/3 to 4, we scale 1/3 to 1 first by doing times 3. And then now that this is 1, you multiply by 4, the same number you see there. So this red 12 that we're after is created by doing the dividend 4 multiplied by the reciprocal of the divisor times 3. And we multiply those together and we get that missing 12 we're looking for. Same thing's going to happen here, right? We have a 1/5 divided by 1/3. So the thing we're looking for will be 1/5 times 3. That's going to be that 3/5 that we're trying to find. Right, we've got a pattern. 8 divided by 4/3. We'll scale 4/3 to 1 first by multiplying by its reciprocal, and then times 8 to get it back up to 8. And put those together. dividend times reciprocal of divisor. And we get that 6. That should be red, just to be consistent. Same thing's going on here, even when they're all fractions. Let's focus on these numbers here. To scale 4/3 to 2/5, we first scale it to 1 by multiplying by 3/5 and then multiply by 2/5. So the number that's here is equal to the dividend, and then the number that's there is the reciprocal of the divisor, and you multiply those together to get the answer that we're looking for. Happens again here. Happens again here. Happens again here. A bunch of examples. Maybe we did too many quotative division examples, but I think I'm ready to generalize. So when I'm doing A divided by C over D, where A could be any number, and I'm doing a quotative conceptualization, then I know I'm trying to answer this question. How many copies of C over D will be equal to A? Right, this is the quotative question that you ask when you see a division. How many copies of the divisor make the dividend? And we're going to do this in a two-step process. I'll keep all the... Let me copy this and do it in 2 steps. Well, there we go. Okay, the first thing you want to do is scale C over D to 1, and we know that reciprocal will do that. Then, so this now is equal to 1, but I'm trying to get it to A. So if I multiply 1 by A next, that'll accomplish it. So in other words, the answer to this question is A times D over C. That's the scale factor. So summarizing, putting these together, with a quotative interpretation, we've justified that A divided by C over D, we're looking for a scale factor, and that scale factor is calculated by doing A times D over C. And you can see the invert and multiply algorithm happening here as well. So backing up to the end of our partitive discussion, similarly, we saw the invert and multiply algorithm occur. Of course, we also see most people will say the invert and multiply algorithm should look like this. A divided by C over D is equal to A times D over C. Notice that I have D over C times A instead. When you think of the traditional rule of multiplier and multiplicand, I like this ordering better, but since in the end multiplication is numerically commutative, you could just write it in that order instead, and you have the invert and multiply algorithm numerically. Okay, and that wraps up division with non-whole divisors, both quotative and partitive, and how they both justify or lead to generalizations that are the invert and multiply algorithm.